Let us have a look at the outcomes for this video. In this video, the focus will be on basic results regarding lines and angles. This will be done in Lesson 1. Secondly, we will consider basic results regarding triangles. This will be in Lesson 2. And finally, we will consider congruency of triangles in Lesson 3. In Lesson 1 of this video, the focus will be on basic results about angles and lines. Let us consider the outcomes for Lesson 1. In this lesson, the following aspects of angles and lines will be reviewed: angle terminology, classification of angles according to size, adjacent, complementary and supplementary angles, vertical opposite angles, perpendicular and parallel line segments, and finally corresponding alternate and co-interior angles. We will start by looking at some definitions and terminology linked to angles. Here we have two representations of angles, and in this case it is very important to indicate which region of the representation is linked to the angle. You can see in this case, this particular region inside. There is also a region outside that can be associated with an angle. So as to avoid confusion, we label angles in general. Also, in general, angles can be measured with a protractor. Furthermore, we measure angles in degrees, which is written as the superscript little circle symbol that you see on the screen. For example, here we have an angle which represents 70 degrees, which is the angle QPR, and this is one way of representing this particular angle using the symbol in front. Note, angle QPR, and the degree sign is clear with the 70 in this case, so we say this angle is 70 degrees. Similarly, the angle ABC is 285 degrees. And here we have a representation, a labeling of this particular angle with respect to the line segments AB and BC, as indicated. Also, we can view an angle in general as the union of two rays or two line segments which have a common endpoint. Now let us consider these two representations once more. Here we have two line segments AB and BC, and the common endpoint is B in this case, and this is where the angle resides. And as indicated, we have labeled the angle in this case representing 285 degrees. Also in this case, we have two rays, PQ in this direction and PR, and the common point in this case is P, which then denotes the angle or assists with denoting the angle 70 degrees as indicated. The alternative notation for angle representation is where we have the 3 points R, P and Q, for example, with the little hat symbol indicated with the center symbol to indicate that this is where the angle actually resides. Or we can just represent the angle as angle P in this particular case. Or we can write P hat, which means this is the angle which resides at this particular point P. The common endpoint is known in general as the vertex of the angle, and either the rays or the segments, the sides or arms respectively of the angle. So here we have, for example, the arms of the angle AB and BC, and since we have used rays in this case to represent the angle 70 degrees, we talk about these rays as the sides of the angle which resides at the vertex P in this particular case. Note that we can also view the angle ABC as the union of the line segment AB and the line segment BC. Similarly, the angle QPR can be viewed as the union of the ray PQ and the ray PR. Note also that the order of the first and the last symbol can be interchanged without affecting the representation of the angle. In other words, this can also be described as the angle RPQ instead of QPR. Similarly, the angle ABC can be described also as the angle CBA, as long as the symbol in the middle or the vertex stays exactly the same. Next, we consider classification of angles according to their size. In all cases, we will represent the angle BAC as indicated with the segments BA and AC used to do so. And note, in this case, in general also, one can denote an unknown angle by a symbol. In this case, we use the symbol theta, and normally Greek letters of the alphabet can be used to do so. So we refer to this as the angle theta, of course, represented as the angle BAC in this case. Now, in this particular case, we say that the angle theta is an acute angle. This means that the angle, the size of the angle, lies between 0 degrees and 90 degrees, strictly between 0 degrees and 90 degrees. Also, the next representation is of a very important type of angle, and this is why we have a specific representation here, a little square that is formed to indicate or denote the angle theta in such an instance when the angle is 90 degrees. We refer to this as a right angle. So whenever the angle, the value of the angle is 90 degrees, we refer to that as a right angle, and we denote it in a very special way, as you can see on the screen. The next type of angle according to size will be when the angle theta is obtuse. That means that the size of the angle lies between 90 degrees and 180 degrees, strictly between. The next representation is that of a so-called straight angle theta. This is when the value of the angle is exactly 180 degrees, which represents then a straight line as indicated. That's why we have the name straight angle associated with this particular situation or representation of an angle theta. Next, we have an angle which lies between 180 degrees and 360 degrees, the angle theta as indicated, still using our two line segments BA and CA, for example. And in this case, we refer to this angle theta as a reflex angle, an angle which lies between 180 degrees and 360 degrees. And finally, we have the specific case of the angle with a size of 360 degrees, and in such a case, we refer to such an angle as a revolution. Theta equal to 360 degrees, one full cycle, or a revolution. We will now introduce the concepts adjacent, complementary, and supplementary angles. Let us have a look at this particular representation of two angles alpha and beta as indicated on the screen. We say that alpha and beta are adjacent angles, and this is because, this symbol can be read as because, first of all, they have a common vertex B. You can see this from this representation. Also, they have a common side BD as indicated. BD is common to both angles alpha and beta. And finally, they are on opposite sides of the common side BD. Alpha is above and beta is below the common side BD. Also, if we have this particular situation where the sum of the two angles in such a case is exactly 90 degrees, we can add a specific description as alpha and beta are then complementary angles. So in such a case, alpha and beta will be adjacent complementary angles. Adjacent according to what we have described, but also the sum of the two angles is equal to 90 degrees, and this is referred to as then complementary angles in such a case. Let's have a look at this particular representation where the sum of two adjacent angles alpha and beta adds up to 180 degrees. Then we refer to these angles as supplementary angles, and we can also describe alpha and beta in such a case as being adjacent supplementary angles as discussed before. We will now consider the concept vertically opposite angles. Assume that the line segments AB and CD intersect at the common point E, as indicated on the screen. And let us indicate the angles alpha, beta, omega, and theta as shown in this diagram. Note that in general, unknown angles can be shown by the small letters of the Greek alphabet. In this situation, we have that alpha and omega are vertically opposite angles. Vertically opposite, as can be seen from this diagram. Similarly, beta and theta are also vertically opposite angles. Beta and theta, as can be seen. Also note that alpha can be represented as 180 degrees minus beta. Why is that? Because the sum of alpha and beta, the two angles alpha and beta, is equal to 180. Note that the line segments CD represent the straight angle of 180 degrees as discussed before. So the sum of the two alpha and beta is 180. Therefore, we can say that alpha is equal to 180 minus beta. Similarly, the angle omega is also equal to 180 minus beta, since the sum of omega and beta is 180. Now this is because we have that the line segment AB represents a straight angle. Therefore, we can deduce that the angle alpha is equal to the angle omega, because both of them are equal to 180 minus beta. Similarly, we can show that the angle beta and theta are equal. Both of them are equal to 180 minus alpha in this case, because beta in this case and theta, okay, together with the line segment AB, which is 180, means that both are equal to 180 minus alpha in this case. Thus, we have deduced here that if two lines intersect, then vertically opposite angles are equal. The concept of perpendicular line segments play a very important role in Euclidean geometry at the school level. So let us have a look what this means. Here we have two line segments AB and CD, and the intersection point of the two line segments at E. Now we say that the line segment AB is perpendicular to the line segment CD if one of the four angles at the point of intersection E is a right angle. Note the symbol that represents the idea or the concept of perpendicularness of two line segments. And note the way that we indicate this. So we know that the angle CEB, or BEC for that matter, is 90 degrees. So a 90 degree angle, it represents the perpendicularness in this case. And note also the way that it is shown as a little, sort of square with the vertex E, or a rectangle for that matter. Now, the challenge here is to answer the question, why are the other three angles in the figure above also right angles? Note that we have three other angles, CEA, AED, and DEB. So if we say that the two line segments are perpendicular, then all four of the angles as indicated will be 90 degrees. Why is that? You have to think of the idea of a line segment which represents a straight angle. Now this is a hint for you to consider then and answer the question, why are the other three angles in the figure above also right angles? Now, right angles can be represented in different ways and it occurs in different situations. One of the most common situations where we will meet the idea of perpendicular line segments is when we have a triangle, say the triangle GPH, and here we have the angle GPH as 90 degrees indicated, so we know that the line segments GP and HP are perpendicular. Also we can see this particular diagram, note this may be the horizontal level indicated by the line segment LK, and we may have here line segments KI and JI as indicated, the common point I, and if this angle is 90 degrees, we can see that the line segment IL is perpendicular to the line segment LJ or LK for that matter, and this will then normally indicate the height. I is the height above the ground level if LK represented the horizontal ground level, for example. Here is another case where the line segments are perpendicular. That's the line segment TU and the line segment MN. This is when we consider quadrilaterals, and later on in this video series we will consider this in particular in the context of quadrilaterals. And here the line segment TU will represent then the distance between two parallel lines or parallel line segments FQ and MN, for example. And here we have the 90 degree angle as indicated before. At the point U, and the line segment TU is perpendicular to the line segment MN. Next we define very important sets of angles linked to line segments in general. These sets are referred to as interior, exterior, corresponding and alternate angles. Let us have a look at this situation. Given two line segments AB and CD and a so-called transversal line segment EF cutting both line segments as indicated on the screen, then we would like to define these types of angles that are displayed on the screen. First of all, we will define certain positions of angles relative to the line segments AB and CD, and note that these two line segments are not parallel in general. These are just two line segments AB and CD with no point of intersection in this particular region as indicated. Then we have a transversal or a line segment EF that runs across, that intersect both the line segment AB and CD as indicated. We define positions as follows. With respect to the line segment EF, we have an angle indicated as angle 1, which is above AB and to the left of the line segment EF, and similarly angle 2 is above and to the right, angle 3 is below AB and to the left, angle 4 is below and to the right, and similarly we've defined the positions of the angles 5, 6, 7 and 8 as indicated relative to the line segments EF and CD in such a case. This allows us then to define these concepts that we have above: interior, exterior, corresponding and alternate angles in general. First of all, the interior angles in such a situation will be the angles 3, 4, 5 and 6. Look at this, 3, 4, 5 and 6. Why are they called interior angles in such a case? Okay, that is the angles that lie between the line segments AB and CD. Can you see? 3, 4, 5 and 6, those angles lie between line segments AB and CD in general. The concept of exterior angles are defined similarly as those angles that lie outside the line segments AB and CD. That is, in this case, the angles 1, 2, 7, and 8. Let's have a look. 1, 2, can you see it's outside of AB, and also 7 and 8 is outside of the line segment CD. These are referred to as exterior angles. Next, we consider pairs of corresponding angles in such a situation. Now, here we have indicated the pairs of corresponding angles. Now, why are they called corresponding angles? Have a look at the angles 1 and 5, for example. 1 and 5, look at the labeling. Above left and above left. Exactly the same labeling with respect to the line segments as discussed before. So these two are corresponding because it's both above and to the left of the line segments AB and CD respectively. Angles 3 and 7 are also corresponding. 3 and 7. Can you see both labeled as below left? Below and to the left of the line segments AB and CD respectively. Similarly, the angles 2 and 6, above right and above right, with respect to the line segments AB and CD, that's why they're called corresponding angles. And also the angles 4 and 8. 4 and 8, both below and to the right of the line segments AB, CD, and of course with respect to this transversal line segment EF. That then defines for us the positioning of pairs of corresponding angles. Similarly, we can define pairs of alternate angles. In this case, they are listed as indicated. Let's have a look why they are called alternate angles. 1 and 8 are alternate angles. So let's have a look. 1 and 8. Look at the labeling above and to the left of EF and above AB. Here we have the opposite labeling. That's below and to the right. Below the line segment CD and to the right of the transversal, the line segment EF. Can you see? Opposite labeling. That defines for us, in this case, a pair of alternate angles. Have a good look at the angles 2 and 7, for example. Above to the right and below to the left. That's why they are alternate angles. And also 3 and 6. 3 and 6, below left and above right. And 4 and 5, the angles 4 and 5, below the line segment AB and to the right of EF, versus the alternate angle in this case will be the angle 5, which is above the line segment CD and to the left of the line segment EF. Note also that alternate angles can also be identified by the shape of a Z, and considering the angles that define the shape Z in different ways. For example, we can move from A to the point of intersection, then to the other point of intersection, and then to D. So 6 and 3 will be identified as alternate angles in such a case. And you can check this for all the other pairs of alternate angles in such a situation. Now, the last type of angles that we would like to identify is so-called pairs of co-interior angles. Note that we have defined the interior angles before as the angles which lie between the line segments AB and CD respectively. That is 3, 4, 5 and 6. But those of the interior angles that lie on the same side, for example 4 and 6, and also the pair 3 and 5, will be referred to as co-interior angles. Interior angles that lie on the same side of the transversal or line segment EF in such a case. Let us again consider the situation where we have two line segments AB and CD with a third line segment EF cutting across as indicated on the screen. Now, whenever the line segments AB and CD are parallel, this is the way to indicate that, and the transversal EF cutting across both the line segments, we can say the following about the angles that we've discussed in the previous slide. corresponding angles are equal. In other words, angle 1 and 5 will be the same, 3 and 7 will be the same, 2 and 6 will be the same, and angles 4 and 8 will be the same. These are the corresponding angles we defined in the previous slide. Similarly, alternate angles will also be equal. So angles 1 and 8, for example, 2 and 7, 3 and 6, the Z, and also angles 4 and 5, another Z from this side. Those angles are all equal in pairs. So, finally, co-interior angles will be supplementary. In other words, the angles 3 and 5, the co-interior angles, if you add them together, you get 180 degrees. Similarly, also for angles 4 and 6. So the conclusion then is, when two line segments are cut by a transversal, and these line segments that you start out with are parallel, corresponding angles are equal, alternate angles are equal, and also co-interior angles are supplementary. I think you should be ready now to tackle the problems of tutorial 1. In part 1 we will have 3 problems. Have a look at this diagram. In problem 1 you have to calculate the value of the angle x in this case. This is if x together with 2x and 3x subtend 180 degrees, or the straight line is a straight angle. The sum of them is a straight angle. In the second problem, you have to calculate the values of unknown angles x and y, and consider this diagram very carefully. In problem 3, the angle A is given as 50 degrees, as indicated. The angle ACB is, in this case, 180 degrees, A, C, and B. If the angle ACD is equal to angle DCE, as indicated, both of them are equal to x, the unknown angle, show that the line segment BA is parallel to CD. At this point in time, I suggest that you pause the video, do tutorial 1, part 1, and then come back and view the solutions. Let us briefly look at the suggested solutions for part 1 of tutorial 1. In problem number 1, we had to calculate the value of the unknown angle x in this case. Now, considering this diagram, we know that the sum of x and 2x and 3x, that's the 3 angles as shown, must be 180 degrees, since it represents a straight angle. Adding together, we get 6x is equal to 180 degrees. Dividing by 6, we have solved then for the unknown angle x, namely x is equal to 30 degrees. In problem 2, we have to calculate the values of the unknown angles x and y in this case. Carefully considering this diagram, we notice that the sum of x and the angle 132 must be 180 degrees, since it represents a straight angle. We take notice of this and we capitalize by solving this particular linear equation, making x the subject of the formula, subtracting 132 from 180, we get x is equal to 48 degrees. This means we can substitute now the x value to find the other unknown angle, namely 2x minus 30 degrees. If we do that, calculate, we find that this 2x minus 30 degrees is really equal to 66 degrees. And noticing that the sum of x and y and this particular angle, 2x minus 30 degrees, adds up to 180 degrees, since it also represents a straight angle. This really means that we have only one unknown, y in this case. If we substitute the values for x, namely 48 degrees, and we consolidate, making y the subject of the formula, then we see that y is equal to, in fact, the angle with value 66 degrees in this case. In the third problem, we were given this diagram, and the fact that angle A is 50 degrees, angle ACB is 80 degrees. in the triangle ABC. And we also were given that angles ACD and DCE are the same. Let's say it has an unknown value of x degrees. We have to then show that line segment BA is parallel to line segment CD in such a case. Now we notice that the sum of x and 80 degrees must be 180 degrees since it represents a straight angle. So in this case, by just looking at this particular equation, 180 degrees equal to the sum of 80 and 2x, we have that the unknown angle x is indeed 50 degrees. With this in hand, we notice that angle BAC is equal to angle ACD. We were given that angle BAC is 50 degrees. We've just calculated the unknown angle x to be 50 degrees, and we have then alternating angles or alternate angles in the case of line segments BA and CD. And this really means that the two line segments BA and CD must be parallel. Remember, once we have parallel line segments and a transversal, in this case AC, and these angles are the same, the alternate angles, we know that the two line segments must be parallel. In part 2 of tutorial 1, we consider two more problems. So in problem number 4, we have the following question. Consider this particular figure or diagram, and here we have that line segment AB is parallel to line segment CD, that is given, AB and CD as indicated. Angle B is 40 degrees and angle A is 30 degrees. And we have to determine now with reasons the angle, first of all, ACD, then the angle ECD, ECD. In the third part, the angle ACB, ACB, and finally the angle ACE, ACE. And you also have to answer the following questions. What is the relationship between the three angles of the triangle ABC? And finally, what is the relationship between the angles A, B, and the angle ACE? So A and B, that is given, 30 degrees and 40 degrees, and the angle ACE, which is the outer angle for the triangle ABC. In problem 5, we are given two parallel line segments AB or BA and ED, and also line segments BC and EF are parallel. In this case, you have to show that the angle ABC is equal to the angle DEF, that is ABC and DEF. Those are equal angles. At this point in time, I suggest that you pause this video, do this second part of tutorial 1, and then come back and view the solutions. Let us consider the suggested solution for problem 4 of tutorial 1. Here we have the problem once again, and the first part of this question deals with the angle ACD. We have to find it and give a reason. So in this case, it's clear that angle ACD is 30 degrees because it's the alternate angle of angle BAC. BAC is given 30 degrees. So since these two line segments are parallel, we know that angle ACD is also 30 degrees. In the second part, we have to find the angle ECD. Now, angle ECD is corresponding to angle CBA as indicated, so that must be equal to 40 degrees since we have these two line segments given as parallel. Remember, in this case the two angles are on the same side of the transversal BE with respect to line segments AB and DE, and also on the same side of the segments C, D and BA respectively. So that makes them corresponding, and since these lines are parallel, we know it must be equal. In the third case, we have to find the angle ACB. ACB, we note that the two angles in the first two parts of this problem, namely 30 degrees and 40 degrees, these two angles, if you add them together, we need to answer the question, what must I still add to be able to actually have a straight angle defined by the line segment BE in this case. So in this case we know that BCE is 180 degrees, straight angle, and we have the sum of two of these angles already, two of these three angles, and it's just a matter of finding the third one, that is the angle, in this case BCA or ACB, and we see that we have to subtract the sum of the two angles we already have, namely 30 and 40, from 180 degrees, and that gives us the angle ACB is equal to 110 degrees in this case. In the fourth part, we were asked to find the angle ACE. We already have that. That is the sum of the two angles ACD and ECD, which we already have from the previous parts of this problem, namely 30 and 40 respectively. If we add them, we get this angle to be 70 degrees. In part 5, we have to answer the question, what is the relationship between the three angles of the triangle ABC? Since we have calculated the angle BCA to be 110 degrees, we can add the three angles together, and we see that in this case the sum is 180 degrees. That is the answer to the fifth part of problem 4. And finally, in part 6, we have to determine the relationship between the angles AB and the angle ACE, the so-called outer angle with respect to the triangle ABC in this case. Now if we look at this carefully, we see that this ACE is just the sum of the angles A and B in this case, and we can note then that the exterior or outer angle of the triangle ABC is actually equal to the sum of the two opposite interior angles. Note that this angle A and B are interior angles, and ACE is the exterior angle for this particular triangle, and the exterior is the sum of the two opposite interior angles in such a case. Finally, we consider problem 5 of tutorial 1. In this case, we're given two pairs of parallel line segments, and we have to show that the angle at B is the same as the angle at E in this case. Now in this case, we assume then that the intersection point for the line segments BC and DE is given as G. So let's just indicate G as being the point of intersection for the line segments BC and DE respectively. In such a case, we can now consider the angle DGC, which is critical in the solution of this particular problem. So if we have a look at the angle ABC, then we know this must be equal to the angle DGC. Why is that? Because these two line segments AB and DE are parallel, and these angles are then corresponding angles as discussed earlier. But the angle DGC is also equal to the angle DEF. DGC is equal to DEF, since the line segments BC and EF are parallel, and these two angles are then also corresponding angles in this situation. Therefore, we know that the angle ABC is the same as the angle DEF and that particular case, and this answers the final part of this particular tutorial. In lesson 2 of this video, we will consider some basic results on triangles. Let us consider the outcomes for lesson 2. In this lesson, we will review basic triangle notations and terminology, classification of triangles according to side lengths, the classification of triangles according to the angle sizes, Proof that the exterior angle of any triangle is equal to the sum of the two opposite interior angles. The proof that the sum of the interior angles for any triangle is equal to 180 degrees. And finally, we will review some techniques linked to the proofs in geometry. We will start the discussions on triangles by introducing some basic triangle notations and terminologies. Let's consider the triangle ABC as indicated on the screen. Then we know that the side length AB or line segment AB can be indicated also by small letter c, can you see, which is opposite the angle with vertex C, where we use the capital letter to indicate the vertex in this case. And similarly, side length AC can be indicated by small letter B and BC by small letter A. These are the sides of the triangle ABC. And this particular convention to show the side lengths opposite an angle by the same letter of the alphabet, but the small letter versus the capital letter, is in place throughout for the standard notations linked to the labeling of triangles. Also, A, B and C, that is capital letters A, B and C, are the vertices of triangle ABC, and the angle BAC can also be indicated by just referring to it as the angle A. Similarly, ABC can be denoted by angle B alternatively, and also angle ACB can just be shown as angle C. These are the angles then of this particular triangle. Let's consider some other important notations and terminologies. If we construct a ray AF such that the angles are equal as indicated, in other words it bisects the angle A, then we refer to this particular ray AF as an angle bisector for the angle A. Obviously, one can also construct angle bisectors for angles B and C in such a case. Also, if we have the line segment BG as indicated from the vertex or the angle B down towards the side AC or line segment AC, such that it forms a 90-degree angle as indicated. In other words, BG is perpendicular to AG, or AC rather, then we refer to BG as the altitude or the height for the triangle ABC. That is with respect to the basis or the side length AC in such a case. Now clearly the height can also be constructed in two other ways with respect to the side lengths AB and BC respectively. Also, in this case HC, have a look, HC is constructed in such a way that the side length BA is halved in this case, so HB has the same length as HA. In such a case, we refer to HC as one of the three possible medians for the triangle ABC. So a median then is a line segment which is constructed from one of the vertices, in this case C, to the opposite side of the triangle, where it actually halves the length of that particular side. So we have, of course, two other medians as well that we can construct with respect to the side lengths AC and BC respectively. An important method of classification of triangles is according to its side lengths. In the first case, we will consider the class of scalene triangles. A scalene triangle is a triangle which has sides of different lengths. And correspondingly, you should know that in such a case all three angle measures are different. Here we have indicated for the triangle ABC that all three sides have different lengths. And of course we know the angles will also be different in all three cases. The second important class of triangles
is a so-called isosceles triangle. An isosceles triangle will be a triangle which has two sides of the same length. In this case, we have indicated that with the triangle DEF as the sides DE and EF being of the same length. In such a case, correspondingly the angles D and F will also have the same size. The third class of triangles is known as the equilateral triangles. Now, an equilateral triangle is a triangle where all three sides have the same equal length. Correspondingly, you should also know in such a case that all three angles, the inner angles of the triangle, will be of the same size, namely 60 degrees. And we have indicated, as you can see with the triangle GHI, that all three sides have the same length. The final class of triangles that we will identify is the so-called isosceles right-angled triangles. Now, such a triangle is one where the angle contained within two equal sides is a right angle. Here we have two equal sides, LJ and JK, for the triangle LJK, and this particular angle contained within the two equal sides is a 90-degree angle or a right angle at J. In this case, we know that the angles opposite this right angle will be equal and 45 degrees each. So the angle at L and the angle at K will be 45 degrees. So this then defines the so-called isosceles right-angled triangle. Triangles can also be classified according to the angle sizes. Let us have a look at a number of such classifications. In the first instance, we look at the so-called acute-angled triangle. Now, such a triangle has three acute inner angles, as indicated in the case of triangle ABC. All three angles are less than 90 degrees. The second category will be the obtuse angled triangle. In such a case, the triangle has one obtuse angle and two acute angles. So one angle is greater or equal to 90 degrees and the other two will be smaller than 90 degrees, as indicated. In the third case, we have the well-known right-angled triangle. In such a case, the triangle has a right angle or a 90-degree angle for one of its angles. Also note that the side opposite the right angle is always called the hypotenuse of the right-angled triangle. So in this case, we have the right angle at the vertex J in this case for the triangle JLK, and in this case the side LK will be the hypotenuse, the side opposite the right angle at J. The other two sides then contain the right angle, that is, the sides LJ and JK contains the right angle as indicated on the screen. Finally, let's consider once again the right-angled isosceles triangle. Now, of course, this is a right-angled triangle in which the other two angles are both equal to 45 degrees, as indicated on the screen. Now, both these angles being 45 degrees also defines this to be an isosceles triangle, as we saw on the previous slide. In such a case, we also know that the side lengths LJ and JK will be of equal size. So this then, the right-angled isosceles triangle again, the definition, but with respect to the sizes of two of the angles being exactly the same as we have on the screen. We will now prove the result that the exterior angle of a triangle is equal to the sum of interior opposite angles. We have to explain this and then give a formal proof of this result. Let's have a look at this particular situation where we have a triangle ABC as indicated on the screen. Now clearly the angles 1, 2 and 3 will be the interior angles of this particular triangle. And should we extend the sides AB to D and BC to F, as well as the side CA extended to E, then we create or generate three exterior angles of this particular triangle ABC as indicated on the screen. So here we have the exterior angles, three of them, and we have the three interior angles. So what this result actually says is that whenever we have such a triangle with the exterior angle constructions as indicated, then we have to prove that, for example, triangle BAE, that is BAE, that is this particular exterior angle, is the sum of the opposite interior to interior angles at 2 and at 3. And this is what we've written here. Also, if you look, for example, at the exterior angle CBD, so we're looking at this exterior angle, then this is also equal to the sum of the opposite interior angles for the triangle, namely angle 1 plus angle 3. And this is our second possibility. The third possibility is, of course, if we look at the exterior angle defined as ACF. Now let's have a look. ACF, this is this particular one, the exterior angle for the triangle. This again must be the same as the sum of the opposite interior angles, namely angle 1 plus angle 2. And this is our third possibility. So this proof that we will give now, a formal proof, will prove one such a case, but the same proof of course hold for the other two cases as well. So let's have a look at the formal proof of such a case. We are given any triangle ABC as indicated with the point D that belongs to the extension of the side BC of this particular triangle. We are required to show that the exterior angle ACD is the sum of the two opposite interior angles A and B respectively as indicated. Now how do we prove this? At this point in time we have to proceed by making a construction that will enable us to utilize some of the results that we have seen thus far in order to prove this particular result. So the construction in this case is to draw a line segment CE parallel to the side BA. In this case the side BA will contain the two angles, the interior angles that I need in this case for the result. So I make sure that from the third vertex C I draw a line segment CE but parallel to the side BA. This is the only construction that is necessary in order to prove this result. Now how do we prove the given result that I have to indicate in this case? Well, first of all we notice that we have an angle 1 and an angle 2. In other words, this line segment CE divides the exterior angle ACD into two parts. Now in this case the part which defines the angle 1, that angle is exactly the same as the angle B. And what is the reason? Remember, corresponding angles, if you have two parallel line segments and in this case another line segment which crosses both of them, a transversal, then the angle 1 will be the same as the angle at B. And this is our first part of the proof. The second part of the proof will be to look at the second angle as a result of the construction of the line segment CE. The angle 2 in this case will be the same as angle A. Now why is that? Remember, we had this idea or the concept of alternate angles. Now angle 2 and angle A are alternate angles since these line segments are parallel, that is BA and CE, and therefore we have the second part of the proof in this particular case. Therefore we can say that the sum of angle 1 and 2 is the same as the sum of angle A and B as indicated. So angle 1 plus angle 2 is exactly the exterior angle that we are looking for, the angle ACD, and then this shows that it's equal to the sum of the opposite interior angles, angles A and B respectively. And this concludes the proof of the fact that the exterior angle of a triangle is always equal to the sum of the interior opposite angles. We will now prove a fundamental result for triangles, namely that the sum of the three interior angles of any triangle is equal to 180 degrees. Let's have a look at this situation. This is the statement of the result or the theorem. We're given a triangle PQR, any triangle PQR as indicated, and it's required of us to prove that the sum of the angles P, Q and R, that is the interior angles for the triangle, is equal to 180 degrees. In order to prove this formally, we need to make a construction. In other words, in this case we draw a line segment MN which is parallel to the side QR, or the line segment QR, and this particular line segment MN must contain the third vertex P in this case as indicated on the screen. So MN is parallel to QR and it contains the vertex P in this case. With this in hand, we now prove this result. Assume, to start off with, that the angle P, which is of course the angle QPR, is labeled as angle number 1. Angle MPQ as angle number 2. And angle RPN as angle number 3. Then we have the following. Angle Q, that's the interior angle of the triangle QPR, is exactly the angle 2. It's the same as the angle 2 because it's alternate angles. Angle Q and angle 2 are alternating angles. This is because of the construction MN parallel to QR, and similarly the interior angle at R is alternate to the angle 3. And that again because of our construction. Can you see that NP go down to R and then to Q, it's a Z, so angle 3 and angle R are alternate angles, and angle 2 and angle Q. With this in hand then we can look at the sum of the three interior angles of the triangle, angle P plus angle Q plus angle R. This is exactly the sum of the three angles as indicated, angle 1 plus angle 2 plus angle 3. This is from our previous statement or result. And of course the three angles here is exactly the angle MPN. MPN is a straight line, so we have here the angle 180 degrees, because remember the straight angle is the angle associated with a straight line, and that is equal to 180 degrees. And this really proves the result then, that the sum of the three interior angles of a triangle is equal to 180 degrees. In example 1, we look at an application of the sum of interior angles of a triangle result. In this figure, we have the triangle ABD has a right angle at the vertex D as indicated. C is any point on the line segment BD, again as indicated, and furthermore the line segment CG is such that it is perpendicular to the line segment or the side BA for the triangle, with G of course being part of the side BA. In such a case we have to prove that angle BCG, that's BCG, this angle over here, is equal to the angle A in the triangle ABD. So we need to prove that these two angles are the same. How do we do this? Well, first of all note that the angle BCG, that's BCG, the one we're interested in, is in fact 180 degrees minus the angle B and minus the angle BGC. That is because the sum of the interior angles of the triangle CBG is 180 degrees. So next we consider the simplification of this expression, because we know that the angle BGC is also 90 degrees. Since BA is just a straight angle, and we have that the angle AGC is already 90 degrees. So what is left is 90 degrees, so the angle BGC is also a right angle in this case. So if we substitute the angle BGC with 90 degrees and we subtract from 180, we get 90 degrees minus the angle B as the expression for the angle BCG. Similarly, we have that angle A in triangle ABD is also equal to 180 degrees minus angle B and minus angle D. The sum of the three interior angles of triangle ABD is also 180 degrees. And we know at D we have a right angle or a 90 degree angle. So clearly the angle A can just be expressed then as 90 degrees minus the angle B. Now note that this is exactly what we had before. This really means that these two angles, angle BCG and angle A, must be the same. And this actually shows the result that was required for us to prove. In example 2, we look at an application of the result that we have proven before, that the exterior and opposite interior angles of a triangle correspond in the sense that the exterior angle is equal to the sum of the opposite interior angles. Let's have a look at this particular problem. In triangle PQR, we have that QS, that's line segment QS, is drawn with, of course, R, the one vertex of the triangle, belonging to this line segment QS, as indicated. This defines then the exterior angle for the triangle PQR, namely the angle PRS in this case. Now, if it is given to us that the angle PRS, or the exterior angle in this case, is twice the size of the angle P, the opposite interior angle, we have to prove in such a case that the two opposite interior angles are in fact the same size. How do we do that? Well, we make use of the results that we know. We know from a formal proof that we have seen before that the angle PRS, that is the exterior angle of the triangle, is equal to the sum of the opposite interior angles, namely angle P plus angle Q. Also, it is given to us that this particular exterior angle PRS is twice the size of the one opposite interior angle, namely the angle P, that is given. So by just looking at this particular two equations, we therefore deduce that the sum of the opposite interior angles, that's angle P plus angle Q, must be equal to twice the size of the interior angle at P. Now, if we manipulate this to make Q the subject of the formula, in other words, take angle P across, so we have 2 times angle P minus angle P, which gives us just the angle P, we immediately have the result that was requested to prove, namely that the opposite interior angles in such a situation, or in such a case, will be exactly the same size. I think you should be ready now to tackle a tutorial which deals with the basic results on triangles. Let's have a look at problem 1 of this tutorial. We're given a triangle ABC, and the side AB is extended to the point D as indicated. So BA is extended to D, and we're also given that in triangle ABC, angle B is equal to angle C. So we have an isosceles triangle, and let's say both these angles is Y, and furthermore, the line segment AE bisects the angle DAC. So DAC, that is the exterior angle for the triangle ABC, is bisected by a line segment AE. We have to prove in such a case that the line segment AE is parallel to the line segment BC. In problem 2, we're given a figure where the ray MB and the ray ND are parallel. Furthermore, we have that line segments MO and NO are the bisectors of angles NMB and MND respectively. So can you see bisectors of the angle means that we have two equal angles there generated by this line segment MO, and also for NO we have two equal angles as indicated on the screen. In such a case you have to prove that the angle MON is a right angle, 90 degrees. So angle MON is 90 degrees. So basically prove that the triangle NMO is a right triangle with the right angle at the vertex O as indicated. At this point in time, I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us have a look at the suggested solution for problem 1 of tutorial 2. Here we have the problem again. In this case we have to prove that line segment AE is parallel to the side length or line segment BC. In this case we know that the exterior angle DAC is equal to the sum of the opposite interior angles, the angle B plus the angle C, and in this case it is given that these two angles are the same. So if we express the sum in terms of y, we know that angle DAC is equal to 2y. It's y plus y, it's 2y. But also, since AE bisects the angle DAC, we can see that this particular angle can also be expressed in terms of the unknown angle x. So 2x, which is the same as DAC, is the same as, in this case, 2y, the sum of the opposite interior angles as indicated. So if 2x is equal to 2y, then clearly we have that x is equal to y. So angle x is equal to angle y. And since we have here the angles x and y are alternate angles, we know that correspondingly the line segment AE must be parallel to BC, as we have discussed this before. Alternatively, we can also look at the angle x in the blue part of this particular angle DAC, which is in this case bisected by the line segment AE, and this is equal to y. These two are corresponding angles, which again confirm that the line segment AE in that case must be parallel to the line segment BC, because the corresponding angles will only happen or only occur if we have parallel line segments as discussed earlier. So we have either the one situation using the alternate angles, or the other, the corresponding angles in such a case, to prove this particular result. Let us look at the suggested solution for problem 2 of tutorial 2. Here we have the problem, given two parallel rays as indicated with line segment MB and ND contained as part of these rays respectively. we have to consider the fact that MO and NO are bisectors of the angles NMB and MND respectively, and prove that in such a case the angle MON is 90 degrees. MON. How do we go about it? Well, first consider the sum of the angles BMN and MND. BMN and MND. Since these two line segments MB and ND are parallel, we note from a previous discussion that these two angles are co-interior angles, and so the sum of the two angles, that is BMN and MND, must be equal to 180 degrees. This is our first statement. Furthermore, we're given that the angle BMN is twice the angle NMO. Can you see, since MO is a bisector, it divides the angle in two equal parts, and in this case it means that we have in the place of angle BMN twice the angle NMO in such a case. Similarly, we can replace the angle MND, that's MND, with twice the angle MNO, MNO, since NO is the bisector of the angle MND. So, in doing so, we see that taking a common factor 2 and dividing through by 2, we have that the sum of the angles NMO and MNO must be 90 degrees. So this is really the sum of the two interior angles of the triangle MND in such a case. So the sum of these two angles, interior angles, is 90 degrees. But we know that the sum of the interior angles of a triangle, all three of them, is always equal to 180 degrees. This is the result that we have seen earlier. So this really means that the angle MON, that is the third angle of this triangle MNO, is 180 degrees minus the sum of the two angles, the other two interior angles. And since this is 90 degrees, we end up with the proof of the result that in such a case, the angle MON is a right angle, namely 90 degrees, as was requested. In lesson 3 of this video, we consider congruency of triangles. Let us consider the outcomes for lesson 3. In this lesson, we will review, first of all, the 4 cases of congruency of triangles. In the second part, we will consider some proofs linked to isosceles triangles. And finally, we will review the theorem of Pythagoras. We will start this lesson by considering the 4 cases of congruency of triangles. But first of all, we have to actually explain and define what is meant by congruency of triangles. So here we have it, the definition then. Congruent triangles are triangles which have the same shape and area. So this really means that, amongst others, corresponding sides have equal lengths and corresponding angles are equal. That is for all 3 corresponding sides and 3 corresponding angles in such a case. So let's have a look at the first case where we can say that 2 triangles are congruent. We consider the triangles ABC and DEF. So in this case, if 2 sides and the included angle, interior angle that is, of a triangle are equal, then we can say that the triangles ABC and DEF are congruent. In other words, as indicated on the screen, if the side length AB is equal to the side length DE, indicated on the screen, BC is equal to EF, that's BC is equal to EF as indicated,
And in addition, we have an angle from the one triangle that is equal to an angle from the other triangle as indicated. The angle must lie between the two corresponding equal side lengths as discussed. Then we say that the two triangles are congruent. Also take note of the symbol or the notation that is used to indicate congruency of two triangles. And we say the reason here is two sides, corresponding sides, and an angle in between are equal. Another case where we can say that two triangles are congruent is where we have three pairs of corresponding sides that have equal length. In the case of triangle GHI and KLM, that is the case. In other words, for these triangles, the side length GH is equal to the side length KL, GH and KL as indicated, GI and KM, GI and KM, and finally HI and LM, HI and LM. In such a case, we can say that these two triangles are congruent because of the three sides in each case being equal to the corresponding side in the other triangle. In case number 3, we can have congruency of triangles as a result of two angles and a corresponding side that are equal. So for the triangles OPQ and RST respectively, as indicated, we have two angles, P and S, corresponding angles equal, and then also again two corresponding angles here, Q and T being equal, and also the side lengths OP and RS correspond and is equal. And the reason for this congruency is then two angles with a side that is correspondingly equal between the two triangles as indicated. The final case of congruency is when we have a right angle, the hypotenuse in such a case, and one other side that are correspondingly equal. So in such a case, we have the triangle UVW and XYZ as indicated, which demonstrates this type of congruency. We have the angles at W and Z correspondingly equal and equal to right angles, and then we have the hypotenuse UV and XY, the degree, same length, as well as one other side. In this case we have VW and YZ, the side length YZ corresponds and are equal in length, and we have the reason in this case the hypotenuse, another side, and the right angle agrees or correspond and are equal in such a case. Now notice that in any one of these four cases, if we know that the two triangles in question are congruent, let's for example look at the first situation, then we can immediately say that the angle A is equal to the angle D, the angle B is equal to the angle E, the angle C is equal to the angle F. So in other words, the order of the vertices are very important if we have the result of congruency in place. We can also say, for example, that side length AB must be the same as side length DE, the first and the second, and the first and the second. And similarly, for example, the second and the third vertex BC, that side length BC, must be the same as EF, the second and the third. And so for any other combination of vertices in this particular case, we can see that the corresponding side lengths must be equal, as well as the angles as discussed. You may well ask the question, when will two triangles not necessarily be congruent? There are in particular two such cases which we will now discuss. In the first case, if we have that the three angles of one triangle are equal to corresponding three angles of another triangle, then these triangles are not necessarily congruent. It will definitely have the same shape, but it may have different areas. So that actually rules out the possibility of these two triangles then being congruent if they have different areas. Here we demonstrated this.
In the triangle ABC and DEF respectively, we have corresponding angles are equal. Angle A is equal to angle D, B is equal to E, and C is equal to F. But surely the areas in this case will differ as it is represented, and these two triangles are not necessarily always congruent. Case number 2 is if we have two sides and a non-included angle of one triangle are equal to corresponding two sides and a non-included angle of another triangle. In such a case, the triangles are not necessarily congruent. Let us demonstrate this by looking at the triangles ABC and EFD respectively. In this case, we have two pairs of corresponding equal sides as indicated, but we have also corresponding equal angles which is not included in between the sides that are correspondingly equal. So you see these angles are outside, not included by the corresponding equal sides. In such a case, we have that the two triangles are not necessarily congruent. It normally have different shapes and also different areas, which by our definition of congruency rules out the situation where such triangles will always be congruent. In tutorial 3, you will be given the chance to solve some problems dealing with congruent triangles. In problem number 1, we have pairs of triangles given, two pairs as indicated on the screen, and for each pair of triangles you have to state with reasons if they are congruent or not. Just note that triangles are not necessarily drawn accurately to scale with this particular tutorial. In the second tutorial problem, you have to state with reasons whether the two triangles in each figure below are congruent. You have to name the triangles in each case with their vertices in the correct order. Here we have the first figure. Clearly we have triangle AEB and triangle CED to consider and to check whether indeed they are congruent or not. And in the second figure, it's clear that we have two triangles, and you need to consider whether in fact these two triangles are congruent or not. At this point in time, I suggest that you pause the video, do tutorial 3, and then come back and view possible solutions. Let us have a look at the suggested solution for problem 1 of tutorial 3. In this case, we had to, for each given pair of triangles, state whether they are congruent or not, and we had to give some reasons. Now, in the case of triangles ABC and XYZ given, we have, for example, that angle B is the same as angle Y, as indicated. Also, angle C is the same as angle Z, as indicated. And given in this case is also that the side AC has the same length as the side ZY. But yet, these two triangles are not congruent because side AC, for example, is position 1 and 3 for the triangle ABC. Now, if these two triangles were to be congruent, then this must be corresponding to the equal side XZ, and it is not. XZ, you can see, doesn't have the same side as AC. In fact, AC and ZY has the same side, but ZY is position 2 and 3 of the given triangle XYZ. So in this case, the two sides are equal, but they're not corresponding sides for the given triangles. So we actually then can state that these two triangles are indeed not congruent. Let's have a look at the second pair of triangles. The triangle, in this case, FED and triangle LMP.
K. The order is important in this particular case. Here we have that the side FD has the same length as the side LK. That's indicated on the screen. And also the side FE has the same length as the side LM, also indicated on the screen. And furthermore, we have that angle L is the same as angle F. And these two angles for both triangles will be the angle between the corresponding equal sides. So in this case, we have that the two triangles are indeed congruent, and the reason in this case will be two sides correspondingly equal, and also the corresponding angle between the two sides for each case will be the same. So we have side and the angle and the side as the reason for the congruency in this particular case. Let us have a look at the suggested solution for problem 2 of tutorial 3. In this case, we had to state with reasons whether the two triangles in each figure, this is the first figure below, are congruent. We had to name the triangles as well as their vertices in the correct order. Here we have the triangle AEB and the triangle CED to consider. So in that particular case, we know that side AE is equal to side CE, that is given as part of the figure. And we also have that angle AEB is equal to angle CED. These are vertically opposite angles as discussed before. Furthermore, we know that since the two line segments AB and CD are parallel, we immediately have that angle A is equal to angle D, as well as angle B is equal to angle C. This is because of alternate angles as discussed earlier. But in this case, have a good look. We know that angle A is not necessarily equal to angle C. And these are the first positions for the triangles AEB and CED. And furthermore, we also know that angle B is not necessarily equal to angle D. This is positions 3. So corresponding positions must have must represent the same angle if these were to be congruent triangles. So in that case, we can say then that the two triangles are not necessarily congruent. In the second figure, we again have two triangles, PNR and PQR respectively to consider. Question is, are these congruent triangles, and if so, why? Here we have the triangles then, PNR and PQR to consider. PN has the same length as PQ, the two sides, that is given, and also NR and QR as is indicated in this figure. So we have two equal sides, and furthermore, PR is a common side for these two triangles, so we have three sides are correspondingly equal, and we can state emphatically that the two triangles are indeed congruent. And the reason is, three sides are correspondingly equal. Next, we will prove the result that the angles at the base of an isosceles triangle are equal. This will prove formally. Here we have the situation given any isosceles triangle ABC with side lengths AB and AC equal as indicated in this figure. What is required here is to prove that angle B is equal to angle A. In other words, the angles at the base of this isosceles triangle are equal. The construction that is necessary here in order to prove this result is to bisect the angle BAC using the line segment AD so that D forms part of the basis or the side BC in this particular case. And that we do. So we bisect angle BAC, creating two equal angles as indicated, and D is part of the basis for the triangle, the side length BC for that matter. How do we prove this? Well, we consider two new triangles, namely ABD and ACD. So can you see ABD and ACD in that particular order? The vertices, we consider those triangles, and we have in this case that the side length AB, the length of the side AB is the same as the length of the side AC. We also have that angle BAD is the same size as angle CAD. These were actually generated by construction. So we constructed AD for these two angles to be the same. And furthermore, we have that the side AD is common for both the triangles ABD and ACD. This is a common side for these two triangles. And we note then that we have the situation where two pairs of sides are correspondingly equal, as well as the angle between those two sides for each triangle will be equal. So the reason is then side and the angle and the side correspondingly equal for the two triangles, and we can immediately say that these two triangles ABD and ACD are indeed congruent. Now what does it mean for two triangles to be congruent? Same shape and same area, so they fit exactly on top of each other, and from that we can deduce then that angle B must be the same as angle C for this particular figure. So it proves then that the angles at the base of an isosceles triangle are indeed equal. In very much the same way, we will now prove the converse result to what we have seen in the previous screen. That is, if two angles of a triangle are equal, then the triangle is an isosceles triangle. That is the result in the reverse direction to what we have seen before. So here we have the situation given any triangle ABC with two angles the same. Angle B is equal to angle C, as indicated in this particular figure. We have to prove that the side AB has the same length as the side AC for this particular given figure. In order to facilitate the proof, we again make the construction. We bisect the angle BAC with the line segment AD such that D forms part of the basis, or the one side BC, as indicated. So these two equal angles shown by dots on the screen, we create them by the construction line segment AD such that D is part of BC. And then we go about proving the result. That is, we have to prove that AB is equal to AC in such a case. We're given that the two angles B and C are equal, that we've started out with. We have created or constructed the line segment AD such that angle BAD is equal to angle CAD. These two angles then are also equal. So we got two pairs of correspondingly equal angles for the triangles ABD and ACD respectively. What is obviously also clear from this particular construction is that the side AD is common to both triangles ABD and ACD, very similar to what we had before. So if we consider the triangles ABD and ACD, we have two angles correspondingly equal, as well as a side, a corresponding side that is equal. In this particular case, the corresponding side is just a common side AD. In this particular case, you see the first and the third, and the first and the third, the corresponding, and it is equal. And this is enough to say that these two triangles are indeed congruent. This is one of the four cases that we have considered earlier, which gives us congruency of two triangles. With that in hand, we can immediately say that side AB has the same length as side AC for the triangles as indicated. Look, AB is position 1 and 2, and also here for triangle ACD, side AC is position 1 and 2 as well. So it's corresponding and equal. We will now consider very informally something which will be very interesting, hopefully,
That is the theorem of Pythagoras. So this investigation will be more of a practical nature. So just have a look at what happens here. We start off with a right triangle ABC. And in this case, for the triangle ABC, the right triangle ABC, the right angle will be at C. So angle C will be 90 degrees. If that is the case, we say that the side lengths, small a, small b, and small c for this particular right triangle is such, the side lengths are such that the square of the side length of the hypotenuse is equal to the sum of the squares of the side lengths of the other two sides of this particular right triangle. Now that is just a statement of the theorem of Pythagoras, a very famous theorem. And we can actually practically demonstrate this particular result. And this is what we'll look at next. So hopefully you'll have some cardboard available and a scissors and a measuring tool, and then we can actually demonstrate that this particular result holds. I claim that the square on the side BC, that is, if I take this side length and I square it, I have this particular area that I create, the square area. The square in this case is a squared, that's the area of this pink part, the square on the side BC. If I take this area and I add it to the area of the square on the other side CA, which is obviously linked to the right angle C in this case, then this side length being b, small b, the area in this case will be b squared. So if you add these two areas, you get exactly the area of the square on the hypotenuse side. In other words, the length c squared gives us the area of a square on this hypotenuse side, and the sum of these two areas will be exactly the same as the area here. This is exactly what I'm stating here. Can you see that? So the theorem of Pythagoras can be interpreted as, the sum of two areas corresponding to a third area. That is the sum of the areas of the squares on the sides linked to the right angle C is exactly the area of the square on the hypotenuse side. How can we check this? Well, let's have a look. I would like you to do a construction here. Cut up a square with the area a squared, to start out with, into 4 pieces as indicated. Can you see what we do with this particular square with area small a squared? We cut it up. We first halve that side, so we create 2 rectangles as indicated, and then you look at the diagonal in each case, and you cut this area into 4 pieces, the 4 colors as indicated. You note also the area on the side CA with the area being b squared, and you can cut this part off if you want to, or create a square with this particular area b squared, and then you fit the pieces together and you'll see that you have exactly the area, or you cover the area for a square with the side length C, which is of course then a proof, very informal investigation and proof that the areas do correspond as indicated by this equation, namely that c squared is equal to a squared plus b squared, linking the sides of a right triangle together in a very special way, and this particular linkage is known as the theorem of Pythagoras. We will now consider a formal proof of the theorem of Pythagoras by making use of congruency of triangles. Here we have a statement of the theorem of Pythagoras once again. In a right angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, as we've seen it before. So here we have the triangle ABC, the right triangle ABC with the right angle at A. And for this particular case, we have to prove that a squared is equal to b squared plus c squared, where a, b and c are just the side lengths
as we normally would denote it for such a given triangle ABC. We start out by constructing the square EBCD on the hypotenuse side, or line segment BC in this case. So BC, we construct a square BEDC, right, as indicated, the side lengths being small a in all four cases. To prove the theorem, we have a further construction, that is, we draw DM parallel to BA. So we start at the vertex of the square that we have constructed, and we construct DM parallel to the side of the right triangle ABC, namely AB, parallel to AB, and similarly we construct EF from the vertex of the square E to F parallel, this EF parallel to the other side, the third side of the right triangle, and we create in such a way this line segment HC as indicated, and we have MD or DM parallel to AB, and we have EF obviously now parallel to HC. So we make such a construction, and we consider then the two triangles, the one we started out with, BAC, that's the right triangle, and the triangle EFB. Now I claim that triangle BAC is congruent to triangle EFB, and the reason for that is two pairs of corresponding equal angles and also a pair of corresponding equal sides. Where did we get that? Let's just have a look at the triangle BAC, and the triangle EFB, Now it's clear that the sides EB and BC are equal by construction. That was part of the construction of the square. So that is easy to see. Have a good look at the angle EFB. I claim that this angle is a right angle. This angle is corresponding to the angle HAF, since these two line segments EF and HC are parallel by construction, and also the line segment CAH represent a straight angle 180 degrees, and since the original triangle had the right angle at BAC, or at the vertex A, we know that this particular angle HAF must then also be 90 degrees, or a right angle. Corresponding angles gives us then that the angles agree, that is EFB, and in this case also BAC. So we have a pair of corresponding equal angles, and we have a pair of corresponding equal sides. Now for the other angle to agree, that is BEF, with the angle, in this case HCD, to see that, just have a good look. If we extend this particular line segment EF down to where it meets the extension of the line segment DC, the angle in such a case will be the alternate angle for BEF. Okay, since these two lines, that's line segments EB and DC, are also parallel. It's a square. So that particular angle down here, if we have the extension of this line segment to the extension of DC where they meet, will be corresponding to this angle HCD. So therefore we can say that the angle HCD is equal to the angle BEC, and this then completes the proof for these two triangles to be congruent. But immediately from this we have a very important result, that is that the side AC corresponds and is equal to the side FB or BF. Let's have a look, and that must be equal to B. Remember, AC is just a side length or a side for the right triangle that we started out with, and that has a length small b. So we say that BF, this particular part here, the line segment BF, has a length small b. So let's just remember that for now. We're going to use it a bit later. In a similar way, and this is something that you can check out for yourself, very similar to what we have done just now, we can prove that the triangles BAC is congruent, the triangle BAC is congruent to the triangle CHD, and in the same way congruent to the triangle DME, and we have seen already that BAC, we have proved that, is congruent to EFB. So in the same way we can show the congruency of all four of these triangles. Now note that these triangles really represent the four triangles that you can see, and one of them being the original triangle that we started out with, BAC. And each of them have an area of BC divided by 2. Now where do we get that? Well, if we look at the original right triangle, the area of this is definitely BC, B side length times C side length divided by 2. It's just half the area of the rectangle with area CB or BC. Now in this case then we can add the areas of all four of these together by just taking 4 times this particular expression BC divided by 2, and that is what we will do next. First of all, let's consider the length of the line segment FA. Now FA is the distance from F to A on this particular side length of the triangle ABC. We know that the distance from B to A is small c. We have just calculated the distance from B to F to be equal to small b using the congruency. So clearly that distance is just the difference between C and B as indicated on the screen. Also, the area for this small square in the middle, that is the square MFAH, is just clearly the side length here, which we have seen is C minus B all squared. So the area of the square in the middle is C minus B all squared, okay? And the area of the big square that we've constructed at the start clearly is A squared. That's EBCD. The area of that square is A squared. Putting this together now, we have that the big square, BEDC, the area of that is small a squared. Okay, and if you can express this then as the sum of the parts of this particular square in area format, we say that's the area of the square in the middle plus the sum of the squares of the four triangles, right triangles that is, that we have indicated before. Putting this together, we see that the area of the big square, small a squared, is equal to the area of the square in the middle, that is MFAH, plus 4 times the area of these congruent right triangles that we have indicated or shown before. Now extending this algebraically, just multiplying out, we get C squared minus 2 times BC plus B squared, plus, if we simplify, 2 times BC. This will cancel, and lo and behold, we have an expression on the right hand side here as small c squared plus small b squared, which is exactly the equation which proves to us the theorem of Pythagoras in this particular case. We can also formally prove the converse theorem of Pythagoras, that is the result in the opposite direction. Let's have a look how we do this. The converse theorem of Pythagoras will be if the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the angle contained by these sides must be a right angle. So let's have a look how we prove this. Well, we're given in this case that the result holds. In other words, the square of the hypotenuse side is the same as the sum of the squares of the other two sides. What we have to prove is that the angle B in this case is 90 degrees or a right angle. In order to do that, we construct a second triangle, DEF, where we actually start by considering the right angle E and the sides linked to the right angle DE and EF to have lengths C and A.
So the side length F is equal to C and the side length D is equal to A. Remember, we have the triangle already ABC with these side lengths ABC. So we construct a second triangle where it's a right triangle and the side lengths DE and EF respectively correspond and is equal to the original side length of AB and BC, namely C and A respectively. That's the construction. And in this case we consider the angle E, which is 90 degrees to start out with. We have constructed it to have a right angle at E. And we can then use Pythagoras. Remember, we have Pythagoras theorem. We're trying to prove the converse or the result in the opposite direction. So having Pythagoras theorem available, or that result, we know that E squared is equal to D squared plus F squared for this particular right triangle DEF. Okay, but since we have constructed this particular triangle to have the side lengths DE and EF the same as for the triangle ABC, we can replace the D with A. Remember, that was part of our construction, and also F with C because of these equalities that we have enforced. And since we know that A squared plus C squared is equal to B squared, remember that was part of our assumption here, given that this is the case. We do not know whether the angle B is 90 degrees, but we at least knew that B squared is equal to A squared plus C squared. Okay, we have the result B squared in this case. So we have proved then that E squared is equal to B squared. Alright, so that really means that the distance B must agree with the distance E in this case. So we have that the two hypotenuse sides for the two triangles ABC and DEF have exactly the same length. B is equal to E. That is what we have actually proved now. Once we have that, we can say, but then it means that these two triangles ABC and DEF are indeed congruent because of the reason all three sides are correspondingly equal. And that means that these two triangles have the same shape and the same area. It fits exactly onto each other, which then gives us the proof that we want. In other words, that the angle B must then also be 90 degrees or a right angle. Okay, just note that in this whole proof of the converse theorem of Pythagoras, we have created or constructed a new triangle where the side lengths agreed, C with F and A with D, and we have proved then after that that the side lengths of the hypotenuse sides for the two triangles must then also be the same, and that allowed us to show the congruency of the two triangles, which again gives us finally the result that the angle B is also 90 degrees. Obviously it must correspond and be equal to the angle E that we have constructed for the triangle DEF. There are very interesting sets of numbers linked to the theorem of Pythagoras, and they are referred to as Pythagorean triples. Let's have a look at the definition of a Pythagorean triple. This is a set of three non-zero whole numbers, let's say A, B and C, and it's always represented as a triple, a round bracket with the three positions, first, second and third, separated by commas, and A, B and C placed in those positions, such that A squared plus B squared is equal to C squared. Now immediately you'll see this as the statement of the theorem of Pythagoras for a right triangle with side lengths A, B and C respectively. But the question is, when will we have the case where A, B and C are whole numbers? If that occurs, of course, then we define the so-called Pythagorean triple. It just means that we can construct a right triangle with the side lengths exactly A, B and C in such a case. Let's have a look at some examples of Pythagorean triples. Interestingly enough, 3, 4 and 5. You can construct a right triangle with side lengths 3, 4 and 5 because 3 squared plus 4 squared is equal to 5 squared. Check that. And other examples of Pythagorean triples are 6, 8 and 10, 5, 12 and 13. Check it out. 10, 24 and 26. So the sum of the squares of the first two, or the smaller of the three numbers, will always be the square of the largest of the three numbers in such a case. You may wonder whether we can find infinitely many such Pythagorean triples. Well, that is well known that is the case. There are infinitely many Pythagorean triples in existence. We also know that the Pythagorean triple 3, 4 and 5, as indicated, is a primitive Pythagorean triple. And we can check for other primitive ones as well. Now, what does it mean to be primitive? If it's a Pythagorean triple, it means that the only common factor is +1. So no other number bigger than 1 will divide all three of these numbers representing the Pythagorean triple. Here we have shown also the construction of the corresponding right triangle that is associated with the Pythagorean triples 3, 4 and 5 and 5, 12 and 13 respectively. Let us look at one of many applications of the theorem of Pythagoras. In this case we will use the theorem of Pythagoras to find the missing lengths in a given diagram. Here we have the diagram, and the question is to find the length of this particular line segment indicated as C. First of all, you have to find the unknowns A and B as well for the lengths as indicated. So here we go. First of all, since we have a right triangle at the bottom here, we know that the theorem of Pythagoras means that 4 squared plus 2 squared will be A squared. And, of course, if we rearrange and make A the subject of the formula, just take the square root both sides, we have that A in fact is 2 times the square root of 5. Check that out. If we simplify the square root of 20, we get 2 times the square root of 5. So at least we know the value of A. How can we find the value of B? Here we also have a right triangle. Can you see it's indicated with these right angles as denoted as part of the figure. So we know that A squared plus 2 squared must be equal to B squared, another application of Pythagoras' theorem. And just substituting the values and simplifying, we have again that B in this case is the square root of 24, or 2 times the square root of 6. So we found the value of the unknown B by using Pythagoras' theorem. And similarly we can apply this again, the theorem of Pythagoras, to the third right triangle as indicated, since B squared plus 3 squared must be equal to C squared. And if we simplify again, substituting the values and making C the subject of the formula, we have this is that C is equal to the square root of 33. So we applied the theorem of Pythagoras 3 times in this case to find the unknowns A, B and C from the given diagram. I think you're ready now to tackle a tutorial on isosceles triangles and the theorem of Pythagoras. So in tutorial 4 we will have 3 problems. This is problem number 1. Given a triangle ABC with angle A 30 degrees and angle C 45 degrees, as well as the line segment BD being perpendicular to the line segment AC, or the side of the triangle, we consider E as a point on the line segment AB, or the side AB, such that AE, the distance AE, is equal to the distance ED. Let's have a look. AE is equal to ED if we construct. So we create a little isosceles triangle within the triangle ABC. In that case, calculate the angle ABC as well as the angle ABD. ABC as well as ABD. And finally, for this part of the tutorial, prove by calculating angles that the triangle DEB is equilateral. DEB. And just check again what it means for a triangle to be equilateral. In problem 2, the diagonals of a quadrilateral ABCD cut each other at right angles at the point E. So you have to make a little construction yourself to indicate this particular result. With that in hand, prove that this particular equation is valid. AB squared plus CD squared is equal to AD squared plus BC squared. So make a little construction and prove this particular result. In the third problem, we have to use the theorem of Pythagoras to find the missing lengths in the given diagram. So here we have a diagram, some information, there's a right angle, there's some side lengths being given, and there are unknown lengths y and x. And you have to find these unknown lengths making use of the theorem of Pythagoras. At this point in time, I suggest that you pause the video, do tutorial 4, and come back and view possible solutions. Let us have a look at the suggested solution for problem 1 of tutorial 4. Here we have the problem once again, and we have to, in the first part, calculate the angles ABC and ABD respectively. Now clearly angle ABC is 180 degrees minus the sum of the other two interior angles. And ABC, the other two interior angles, are given as 30 degrees and 45 degrees. Adding this together and subtracting it from 180 degrees, we have the result here that the angle ABC is 105 degrees. Remember that the sum of the three interior angles of a triangle is always 180 degrees. Also, the triangle BDA is a right triangle, since it was given that this angle BDC is 90 degrees. So obviously ADC represents a straight angle, so the angle BDA will also be 90 degrees. In that case, we know that the angle ABD will be 90 degrees minus the angle at A, which is 30 degrees. So we have 90 minus 30 degrees, which gives us 60 degrees for the angle ABD. Okay, that takes care of the first part of problem 1. In the second part, we know that if we would like to show that angle or triangle DEB is equilateral, that's D, E, and B, we need to show that all three the interior angles are equal to 60 degrees. Note that from the first part, we already know that the angle EBD is 60 degrees. But we also know that angle BED is the exterior angle of the triangle EAB. And what do we know about EAB? It is isosceles. It was given in this case. So we know that if this is 30 degrees, the angle EDB, or the angle EDA rather, will also be 30 degrees. So the sum of the opposite interior angles will be 30 plus 30, which then gives us the angle BED also to be 60 degrees. And this is exactly what we have here. Okay, the exterior angle BED is the sum of the opposite interior angles EAD and EDA, which is 30 degrees plus 30 degrees, which gives us 60 degrees. Remember, isosceles triangle will have equal angles at the base, in this case the side AD. So we have also that the angle EDB, this is the third interior angle, will be 180 degrees minus the sum of the other two interior angles for the triangle BED. And since both of them are 60 degrees, it's just a matter of calculating and confirming that the third interior angle is also 60 degrees. Since all three, the interior angles of the triangle DEB then is 60 degrees, we know that it must be equilateral because the side lengths, all three of the side lengths for that particular triangle will then be equal. In the case of problem 2 of tutorial 4, we have a quadrilateral ABCD as indicated. And we know that the diagonals DB and AC of this quadrilateral intersect at a point E, and this intersection is such that all four angles at the point of intersection will be right angles. So we have to prove this particular result with respect to the side lengths AB, CD, AD and BC for this particular quadrilateral. Let's see how we do that. First of all, notice that by the theorem of Pythagoras, AB squared is equal to AE squared plus EB squared. It's AB squared, that's one side of the quadrilateral. This is the hypotenuse for the right triangle ABE, is equal to AE squared plus EB squared. Similarly, we know that CD, the other side length of the quadrilateral, as a hypotenuse for the right triangle DEC. Note we have 4 such right triangles now with respect to the point of intersection E. We have that DC squared is equal to EC squared plus ED squared. That's also by the theorem of Pythagoras. Now, putting this together, let us sum the squares of AB and CD respectively. We just replace it with the right hand side expression by using the theorem of Pythagoras to get this particular expression, or equation rather, for the sum of AB squared and CD squared. And now it's just a matter of rearranging the order of the 4 terms of this particular right hand side of the equation. So we take AE squared plus ED squared instead of EB squared. We swap EB squared and ED squared. And we notice that the first 2 terms here, the sum of the first 2 terms, AE squared plus ED squared, let's just have a look at the diagram. AE squared plus ED squared gives us actually the square of the side length of the quadrilateral, that is AD squared, for this particular right triangle ADE in mind. And similarly, for the sum of term number 3 and 4 on the right hand side, we have EC squared plus EB squared gives us the square of the 4th side of the quadrilateral, namely BC squared. If you replace BC squared there for the second bracket and for the first bracket AD squared, we have exactly the result that we were asked to prove. And this obviously is a result of an application of the theorem of Pythagoras. In problem 3 of tutorial 4, we have to use the theorem of Pythagoras to find the missing lengths x and y as given in the diagram. Since we have a right angle as indicated, this becomes a straightforward application of the theorem of Pythagoras. So we have that x squared is equal to 2 squared plus 3 squared from the theorem, since x is just the length of the hypotenuse of the right triangle as indicated. So this gives us x equal to the square root of 4 plus 9, which in fact is the square root of 13. Similarly, we can identify the second right triangle here, and the side lengths 3 and square root of 17 result in the fact that y squared can be expressed as the square root of 17 squared minus 3 squared by the theorem of Pythagoras, and this gives us 17 minus 9, which gives us 8. So y can then be calculated as the square root of 8, or just 2 times the square root of 2 in this particular case. We have come to the end of the video on angles, lines and triangles. Remember, consult textbooks for additional examples. Attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this particular video, and repeat this procedure until you are confident. Do not forget, practice makes perfect. Goodbye and good luck.